Okay. Alright, we're going to go over basic thermostatic operation for an electric water heater. It would be the same for an 80-gallon water heater or a 50-gallon water heater. This particular heater is a Bradford White, but the state is very similar. Not enough difference to make any major difference. First thing we're going to do is verify that we have disconnected the power, set our meter to volts. We have no voltage, so we're okay there. We have the power turned off at the panel box. We always want to verify that. Never take it for granted that the breakers in the panel box are marked correctly, because sometimes they are not. If this were energized, we would have 110 volts on each side of these top two screws. 110 volts there. We would go to ground here and verify that we had 110. We would then come over to this side over here and verify that we have 110 volts there. If we don't have that when we're energized, there's no point in going any further down. The problem is either going to be the wiring, the connections at the top here, maybe one of them has come loose, or there's a problem with the breaker or a problem in the panel box. We have to have 240 volts here before we can go any further on an energized system. In most cases, if you're working on three-phase or 208 volts, it'll be a little different, but in that case, you can call your manager and get some recommendations on that. Typically, the way the upper thermostat works is these two screws and these two wires are always hot. There's always 110 on each one of these for a combined 220 to 240 volts. Besides that, this terminal here, if I were energized right now and went from here to here, I would be energized there at all times as well. That is always hot. What that means is this side of this element would always be carrying 110 volts. And the red wire coming from this screw, which goes all the way down here to this side of this element, would also be hot at all times. It's not going to heat under those conditions because we don't have any power coming in from this side yet, because the thermostat controls that. So while we have 110 volts here, there's no current flowing because this switch has not made yet. Now going back up to the top thermostat, we have 110 here all the time. If this thermostat says, hey, this is just a switch, by the way, just like a light switch, only it's operated by temperature instead of by somebody's fingers. If this thermostatic switch says, hey, my tank is cold, I need hot water, internally it's going to switch. It's going to energize this side which normally, if the switch is off, would not be powered. But if it's calling for hot water, this switch then gets hot, makes this terminal down here hot, 110, giving us a combined voltage here of 220 to 240. That would mean this element we're heating. We can verify that. We're working on a dead system right now, but we can verify that by putting our amp probe. We need this type of an amp probe to properly measure amperage. We would put this on there and get a reading somewhere in the 16 to 18 amp range, I believe, to make sure that we're drawing the proper amperage. Once this element is heating and we've determined that the amperage is good, we could then verify that by turning off the power to the unit once again, disconnecting one side of the wire. It doesn't matter which side, but we have to disconnect one side when doing a continuity or an ohm test. If we have one side connected, we verified that the power's back off at this point. If we have one side disconnected and we put our scale on ohms and read our ohms across the element, we have about 12.80, anywhere 13, 14, somewhere about there. Should be pretty good on a 4,500 watt element on a 240 volt system. The reason we don't want to do this with this wire connected is because we could have a burnout element and still have continuity here. If this thermostat is calling for heat, the continuity would read through the thermostat even though we had no continuity through the element. So whenever we're testing elements, top or bottom, we want to do that with one side of the wiring disconnected. It doesn't matter which side. If we're going to do it with the thermostat energized, we would want to do it on this side, because this side would not be hot unless the thermostat were calling for heat. That's just a safety issue. All of this should be done with the power off for safety reasons. We verified that we have the proper amperage. We verified that we have good continuity. And at this point, we're going to assume that we've heated up this top column of water to the point where this switch, this thermostat, has turned off. Now, if the bottom thermostat is at this point calling for hot water, that upper thermostat, once it turns off, remember we said that this side is hot all the time anyway, if this thermostat then decides that this tank is cold, it needs hot water, this switch would close or make, and this side of this thermostat would then be hot, sending another 110 volts down through this side, which completes the circuit, causing the resistance necessary to create heat. So now we would have 240 volts here, and we would verify proper amperage by putting our amp probe around the wire, checking that, making sure we have similar amperage to the upper as we did to the upper element. In that case, everything would be fine. One thing we want to do, when we're doing these tests and we are altering the temperature of the thermostat to get the units to fire so that we can check the amperage, we want to make sure that we return them to their original state so that we don't have an ASR sometime in the future because the water is not at the temperature it was prior to our arrival. So we want to make sure that we leave it the way we found it. Beyond that, we want to make sure that the relief valve on the inside of the tubing on the relief valve coming off of here is dry, that it hasn't been dripping. We want to test the pressure in the house and make sure that we don't have high pressures. Keep in mind that the pressure in the daytime is going to be different than the pressure at nighttime, so our nighttime pressures, if we're on the threshold of acceptability during the daytime, we might exceed the threshold of acceptability at nighttime when there's no people, no persons in the neighborhood using water. The pressures might be significantly higher. That's basically electric thermostatic operation in a water heater. The only ones that would be different are some of the American water heaters that are a little more sophisticated. They have a control box on top. They don't use thermostats. They use thermistors, which are electronic. In most cases, if there's a problem with one of those, our recommendation would be just to replace the heater with something that's actually has replaceable parts rather than circuit boards and things that we don't seem to have access to. So at this point we would verify that we have put our thermostatic temperatures back the way we found them on the top and bottom. We would put our cover back on here, our insulation layer back on, and then put the cover back on. One of the things I always like to do when I take a cover off, as soon as I take that cover off, is take that cover screw and put it right back in the hole that it came out of, so that if I'm in a dark, dank basement or in a crawl space and I happen to drop that screw, it's really hard to find. If I put it back where it came from, I know where I'll find it when I need it. That's kind of it for thermostatic electric water heaters. If you have any other questions about that, please give me a call. Thanks.